Every single day, an enormous amount of energy hits Earth from the sun. In fact, just 1 hour of sunlight provides enough energy to power the entire world for an entire year. And yet, for the longest time, humanity struggled to harness this incredible force in a clean, efficient, and practical way. That is, until we figured out how to turn light into electricity using nothing more than silicon, a few carefully added chemical elements, and a bit of clever engineering. The result? Photovoltaics, the science of converting sunlight into electric current using solar cells. No moving parts, no fuel, just light and physics. But how does it really work? And even more surprisingly, how do solar panels keep generating electricity during winter when it's cloudy, cold, and daylight is limited? Let's start at the very beginning. Sunlight isn't just light. It's a stream of particles called photons. These photons carry energy. When they hit the surface of a solar cell, usually made from silicon, they can knock electrons loose from their atoms. But not all silicon is the same. In fact, a solar cell has 2 layers of silicon, each doped with different elements to give them specific electrical properties. One layer is doped with phosphorus, which adds extra electrons. This is called the N-type layer. The other is doped with boron, which creates gaps or holes where electrons would normally be. This is called the P-type layer. When these layers are combined, they form what's called a p-n junction, which creates an internal electric field. Now, when a photon from sunlight hits the solar cell and knocks an electron loose, that electric field pushes the electron in one direction, out of the cell and into an external circuit. This movement of electrons is electricity. The more photons that hit the panel, the more electrons get knocked loose, and the more electricity is produced. But a single solar cell doesn't produce much, about half a volt of power. So, in practice, solar panels contain many cells wired together, covered in glass, and mounted in a durable frame. On your roof, that might be 10 or 20 panels. In a solar farm, it could be thousands. But there's a catch. Solar panels produce direct current, DC, while most homes and appliances use alternating current, AC. That's why every solar system includes an inverter, a device that converts DC to AC so it can be used in your house or sent into the power grid. So far, so good. But what about winter? Most people think that solar panels stop working when it's cold or cloudy, but that's simply not true. In fact, solar panels don't need heat, they need light. Even diffused or indirect sunlight contains photons, and as long as photons are hitting the panel, electricity will be generated. Yes, it's true that performance drops in winter because there's less sunlight, shorter days, and more cloud cover. But panels still work. In fact, solar panels often perform better in cold weather because heat can actually reduce the efficiency of the semiconductor material inside. So even if there's snow on the ground and the sky is overcast, as long as some light is getting through, solar panels will still produce power. And if the panels are clear of snow and the ground is reflecting light upward, they may even get a performance boost thanks to albedo, the reflective property of snow. Of course, winter production is lower. A typical solar panel in a northern climate might produce 4 or 5 times more energy in July than in December, but it never drops to zero. Solar cells respond to light, not heat, and that's a crucial distinction. But what happens at night? Obviously, no sunlight means no electricity generation. That's where batteries come in. Most modern solar systems include lithium-ion batteries to store excess energy during the day and release it after sunset. These systems can power your home well into the night, especially when combined with smart energy management systems that prioritize critical loads and optimize usage. And if there's not enough sunlight for several days, most homes stay connected to the grid, allowing them to draw traditional electricity when needed and send back any surplus solar energy during peak times. This creates a hybrid system, part solar, part conventional, which increases reliability and energy independence. There's another common misunderstanding. People often confuse solar panels with solar thermal systems. Both use sunlight, both are mounted on rooftops, but they're not the same. Photovoltaic panels produce electricity, while solar thermal collectors heat water. If you have a solar pool heater or a hot water tank powered by the sun, that's thermal. If you're charging your phone using solar panels, that's photovoltaic. Now let's talk about lifespan. Modern solar panels last a long time, typically 25 to 30 years or more. Most manufacturers guarantee that after 25 years, the panel will still produce at least 80% of its original power. They're built to withstand hail, wind, snow, and high temperatures. They require almost no maintenance. usually just the occasional cleaning to remove dust or bird droppings. From an environmental perspective, solar energy has one of the lowest carbon footprints of any energy source. Of course, there are emissions from manufacturing and transporting the panels, but over their lifetime, panels generate far more energy than it took to produce them, typically within 2 to 4 years. And when they reach the end of their life, most solar panel components, including the glass, aluminum frame, and even some silicon, can be recycled. Recycling processes are constantly improving, making solar energy not just clean, but also increasingly circular. Today, solar power isn't just a niche for eco-conscious homeowners. It's becoming a mainstream energy source used in homes, schools, businesses, and even entire cities. There are community solar projects, floating solar farms, and solar panels built directly into buildings and windows. New technologies are developing every year, including thin-film panels, perovskite cells, and flexible solar sheets. Solar isn't perfect. It's not constant. It's not always efficient. But it's clean, quiet, scalable, and remarkably reliable, even in the heart of winter. Subscribe us for more videos.